Alright, so good afternoon, everyone. So, without any further ado, let's start today's session. So, I will share my screen first. Hmm. Okay, so I hope the screen is visible to everyone and I am audible also. Can someone please confirm?
Yeah.
Yes.
Thank you. So, this is so my name is Mayank Anupam. First of all, this course is actually analog IC design, and it's taken by Professor Sankaran Anirudhan. Okay, it's from IIT Madras. My name is Mayank Anupam, and I will be the tutor for this course. And I am from electrical engineering, IIT Kanpur. Also a PMRF scholar. Fine. So yeah, so in this week, basically this session we will be covering the portions that were covered in week 6. So, but before that, let I will try to motivate all of you about some intuitions of the poles and zeros. So this I feel is very important from the point of view of interviews also, and that is why
Sir,
yeah.
sir, actually, I have few doubts from the previous years for previous week's lectures, like few doubts in terms of the problems which were given.
Yeah,
So some
go
basic
on.
things were,
Yeah, so
huh?
ask.
Yes.
Yeah.
So can you please share the week 3 assignment which was given week 3 or week 4? I think.
Okay, so
Yeah, week four, sir.
hold on. Let's see. Week 4, right?
Hmm.
Yeah. So is it visible?
Yes, is it visible? Yeah.
Cool. So week 4, you're saying?
Hmm.
Yeah.
Uh, yes. So in this set of problem,
Mm-hmm.
like when we are told to calculate the non-dominant pole, that
Mm-hmm.
P2, when we are told to calculate, like what formula we have, like after all the intuition and all, when we are going for the formula, what we have that P2 is something like GM2 into C by C plus 1 plus G naught 2 by CL plus that series combination of C and C1, like that it is the formula of P2.
Correct. Something
Yeah.
like that. Yeah.
So one of my question is, sir, for this CL,
Mm-hmm.
what we should put, like should be it be this 40 femtofarad, or only, or the 40 femtofarad and this 1 picofarad will be in parallel, like will be 1040
Okay.
femtofarad,
Okay.
like.
Yeah. So basically, you see, uh, so the two-stage op-amp. So the question. Read the question. It's okay. The two-stage op-amp figure 1 is used in the unity gain follower shown in figure 2. Right. This is given. So this
Hmm.
particular op-amp is going to be used in this particular configuration. Okay.
Yes, yes.
Right. The transconductance GM and the output conductance G0 of the individual transconductors are shown in figure 1. Okay, basically this op amp, this two stage mirror compensated op amp is kind of collapsed in the form of a block level representation, which is
Uh-huh.
shown here, right?
Yes,
Fine.
yes.
Now the op amp is mirror compensated for a phase margin of 60 degree in unity gain configuration. Okay, so this is basically the condition where
Yes,
this is unity gain configuration, right? And this
yes.
op amp is mirror compensated to be used as in this particular configuration. Okay, so when this it is saying that the op amp is mirror compensated for a phase margin of 60 degree in unity gain configuration. So this particular op amp that is in figure 2, this whole block is basically unity gain is basically compensated for unity gain configuration with a phase margin of 60 degree. So naturally, when you want to calculate the pole positions and phase margin and everything about this op amp, you'll have to take into consideration these two guys here. Okay,
Okay.
because this op amp is not going to be used just like that. It's going to be loaded by something, right?
Yes.
And the loads
So
are
the
here.
load capacitance will also contain this 1 picofarad also in its
Right, definitely, yes.
configuration. Yes.
Yes.
So then, sir, my question was like, how in the videos I have learned like this from the phase margin calculation and all the 60-degree phase margin calculation,
Mm-hmm.
some equation comes like omega u by p2 is equals to some 16 degree. So when it comes like that, then when we are putting the equations like omega u, we are putting gm1 by cc. For p2, we are putting the all that calculation, all the formula we are putting. So after that, in that cl configuration, I am putting some 1040 femtofarad, or the c1 whatever is the 10 femtofarad is giving and all. So whenever I am calculating, I have got a result nearly some 9 the for the uh, calculation of c, whatever is there, I have not got that thing, whatever result is there. So I have checked out my calculations and all after putting there, so the result is not coming. So like I have a doubt some of my approach is proper or not.
Okay,
So if
let's
you can
solve this
please
question.
solve, yeah,
So
that
let's
will
solve
be
this question. Okay.
Sir, I also have a similar query with this question itself. Like, I also got something around 920 femtofarads as my answer,
Okay.
the second answer, and in the answer range it was somewhere around 820 to 840 femtofarads.
yes.
And
Actually, my
many other
answer also
people
comes like
also even
927. Yeah.
commented about this.
Okay. So let's solve this question. Okay.
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 Yes.
Let's do it. So stop sharing this. Okay. Okay. Let's do this. Yeah. So it is visible, right? My screen is visible. Correct.
Yes, sir.
Okay. So what? Okay. Let's. So what was the question basically? Uh, you have a GM. You have this block, right? So this is a small digression, right? Assignment week 4. Cool. Let's do this. So we have this we have this block level op amp. Okay. Okay. Which is kind of connected in unity gain configuration in this way. This is RL and this is CL, and here we have our input, right? And this op amp is basically a collapsed version of this two stage mirror compensated op amp. Okay, I guess this was the figure, right? And what were the values? The values were basically we have this gm1, this is equal to what, 20
20
micro,
microsieverts.
and
Point 0.2. G not 1 is point 0.2.
Point two.
yeah, so one second, one second. Okay, so this is point 0.2 microsiemens, and this is g naught 1. What is c1? 10 femtofarad, right? And what is c we do not know, this we do not know, right? And gm2 is basically 80 microsiemens, yeah, 80 microsiemens, and this guy here is zero point 0.8 microsiemens. This is g naught 2 is equal to 0.8 microsiemens. Okay, and this here is 40 femtofarad. Fine. CL is equal to 1 picofarad and RL is equal to what? 1 by 7.2 microsiemens. Okay, fine. So now what is the question? Determine the overall DC gain of the op amp. So that is easy, right? First of all, what is given in
Yes.
the question? It is given in the question that this op amp here, is basically compensated to have PM is equal to 60 degree in what? Unity gain configuration, right? Okay, alright. So let's do after that. Yeah, so what is DC gain?
GM1, GM2 by G not 1, G not 2.
Cool. So first is DC gain, that is basically GM1 I G naught 1 into GM2 by how much?
Jude.
Is it? Think
Yeah.
During
properly.
DC, for calculating DC gain, the capacitors will be open.
Correct?
All the, yeah.
Correct?
So
No,
like
RL will be considered, right?
Yeah,
With Jude.
right. RL has to be considered. So the condition,
Sir,
you see the this is the one which we are considering, right? So we have to open the loop for this one in this manner. So when we open the loop, and this guy which is inside here, this op amp here, is replaced by its version here, right?
hmm,
So that we have to consider it as a whole. Okay. So here we will have to consider RL while DC gain calculation. So what will be the picture in DC gain? So this is basically, sorry, DC gain. So the picture will be what? We'll have this GM1, right? We'll have this G naught 1. There is no problem there. We have this GM2. Okay, then the capacitors are open, right? So CC is gone. This C is gone. This C is gone, right? And after that there is G naught 2 here, but you also have this capacitor RL, right?
hmm.
Sorry, resistance RL. So this also comes here in parallel to this one, RL. And then again CL is also not present, right, in the DC calculations, correct? So
Yes.
this is the condition here, and so this is GM1, this is G naught 1, this is GM2, this is G naught 2, and this is RL, right? So what it will be? DC gain?
RL.
Sir, it will be 60,
No, no,
60
no,
dB.
no. Tell me the expression. So numbers do not matter. Tell me the expression.
U1. GO2 by
GM1 divided by GO1
G1
into
into
GM2
into
2.
divided by
divided
GO2
by
plus
GO2
GL. GL.
parallel
Yeah, so parallel RL means what? They will add in conductance, right?
Plus GL, just plus
Yeah,
GL.
correct. Plus GL.
GO2 plus GL.
Right, exactly. This will be GO2 plus GL, right? Now tell me then, so it doesn't matter what is the value, but let's say we want to calculate the value because that is the whole fuss about, right? So what is GM1? 20 micro, correct? What is GO1? 0.2 micro, cool. Now what is GM2? 80 micro. What is GO2 plus GL?
8 micro.
Correct, because it is 0.8 micro, right? GO2, and RL is 1 over 7.2 microsiemens. So what is GL? GL will be simply inverse of this, right?
Uh, the
yes.
answer will be nearly 10 cube.
Correct. So let's check whether what is the answer. So this is 8 micro, or 8 into 10 to the power minus 6. Okay. So it will be what? This and this gone, this and this gone. So this is 10 and this is what? 100. Correct? So it's a 10 to the power 3. Basically it's a gain of 1000, right? Volt per
Hmm.
volt. Cool. Now let's move on to the second question. What is the second question?
But so the answer is given like it's a 80 dB. It should be
Yeah,
in
so it
60
is
dB.
given.
Yes, sir. Actually, sir, the question was the overall gain of the op amp. I mean DC gain,
Gain of the
and we are
overall DC
calculating
gain
here
of the
the
op amp.
overall circuit gain.
Yeah, so that's a problem, right? Hmm. You'll have to ignore this in that case. RL. Yeah, so
Actually, sir,
that's a
we
confusion.
got this answer and gets 0 marks.
Yeah, I understand, but that's okay. I mean, that happens. That as I told you earlier, also that happens. That confusion occurs whenever, in general, whenever you are asked a question about op amp and it is given that it is basically they generally clarify this part that determine the overall DC gain of the op amp for figure 2, like that, something like that they do. At least in assignment 5 they have done that. Okay, so that happens, it's okay. I mean, no need to worry about that. It's okay. 60, the point is that this is the right means this is the expression. If you understand that, then it's okay.
Hmm. Yes, yes.
Okay, cool. So let's
Yes,
move on to the second part. What is that? Overall transconductance in millisievert. Overall transconductance millisieverts. And what is overall transconductance? So I told you about it, right? So what do you mean by that?
GM2 into GM1 by GO1.
Right. Basically, overall transconductance means the, if you can understand this here, you see this picture here. In this, the transconductance of GM2, you see that this is the first stage is gain block, right? The first stage is simply simply amplifying the second stage transconductance, right? By some factor GM1 by G02, right? That is why the overall transconductance is simply what? GM2 into GM1 by G01. Okay, and what is that? Let's see. This is 80 micro. C1 into what is this? 100, right? And what will it be? 8000 micro C1, which is simply 8 millisiemens. So is that correct? Yeah,
yes,
so it is
yes,
8
yes.
millisiemens.
Sir, but can you please explain the logic behind it? Like, I'm not able to understand the behind logic for this.
Okay, okay. So you see, let's change. You see, this is the second block GM2. Okay, this is a VCCS, right? A voltage
Yeah,
controlled current source, correct?
right.
Right? Now, what is the current that it will be pushing out? The current that
Uh,
will flow out of this block will depend upon what is the voltage appearing here, right?
right.
So it is basically GM2 times whatever voltage we have here. Let's call it V1,
Yes.
right? And this voltage V1, what will it be equal to? This voltage V1 will be equal to what? GM times
GM
G01.
on GM on divided by small go1.
Into whatever we apply here, right?
Yes. V.
Correct. So if you view this whole, this two-stage Miller compensated op amp as a whole block as is presented here, in that case you can say now that when you apply an input V in here, the current that will be pushing out will be corresponding to a GM which is amplified by this factor, isn't it?
Yes.
Now did you understand that?
Yes. Sir, so what's the why do we calculate it only for DC conditions like transconductance? Is it
Yeah, so
designed
that's
only for
what
DC?
I also said it earlier also that it is not actually very correct way to ask this question. I mean, this question doesn't have much significance here. Okay, you are right. I mean, this is actually strictly true only for the DC case. Okay, so but it gives you a sense that basically the overall transconductance is being amplified. I mean, you are able to push in more current for the same amount of voltage. So that this is just for the sake of asking this question. Okay, nothing serious is going on here. And
Okay.
you're right that it is only true for the DC condition. As the frequency increases, the transconductance overall transconductance is going to decrease because the gain of the first block is going to decay, right?
Yes.
Cool. So that's done. Now what is the third question? Determine the value of capacitance in farad. C in farad. Okay. Femtofarad. Okay. Value of C in femtofarad. So what will you do to calculate the value of C?
Phase margin
Correct.
equate to
Uh,
60 degree.
Yeah. Someone was trying to say something else.
from the phase margin equation, we will just evaluate it in terms of the unity gain frequency and second pole because those two are unknown.
Right.
Now,
So
in
let's do
the
it.
yeah,
So we have been given phase margin is equal to 60 degrees, right? And what is phase margin actually equal to when we have this? So we have this scenario, right? We can assume that the first pole appears at a very low frequency, right? And then we have this condition here. So I oh shit. Let's take this figure here. Okay, and then we have the second pole P2. From there we have this 40 dB per decade here. Okay, and this is basically omega u loop. This is omega. This is loop gain in dB. So cool. So this is P1. Fine. This is minus 20 dB per decade, minus 40 dB per decade. Okay. So what? Yeah, we have this phase margin equal to 60 dB. We can assume for this purpose that for this question that this P1 pole P1 is much farther away from this omega u loop. Okay, is that clear?
Yes.
Yes.
Yes,
yes,
Cool, cool, cool. So what is the phase because of this P1 pole? 90 degree, right?
minus 90 degrees.
Minus 90 degree, yes. So let's write it here. Phase phase margin, no, not phase margin, but first phase delay due to P1 at omega u loop is equal to minus 90 degrees, right? Or since we are writing in terms of delay, so let's call it 90 degrees, not minus 90 degrees. Okay. Now, so basically, whatever phase delay we have at this point omega u, whatever phase extra phase we have, that is because of P2, right? Phase delay due to P2 at omega u loop. What is that?
Minus 10 inverse omega loop by P2.
Correct. Exactly. Right? This is omega loop divided by P2, right? Cool. Now phase margin is equal to what? 60 degrees, and that is equal to what? It's equal to, so right in terms of here, so it is equal to 180 degree, sorry,
180 minus
minus, minus or plus?
Plus.
Minus. That means plus minus 90 degree. Plus of minus 90 degree.
And
Minus tan inverse omega u loop by P2.
Minus tan inverse.
is it correct?
And one more, for the zero there will be
sir,
one.
we need
Yeah.
So one more will be added, like minus tan inverse omega u by
minus tan inverse 1 by 4 due to the 0.
Okay, correct. So let's add that. So I didn't write that, but let's add that. Yes. Okay, so this is like this, and from here it again goes here, right? Correct.
yes, sir.
So omega z, right? So what will it be now overall? Is this correct, by the way, the expression here?
No, that thing will also be there, no? The omega u by omega u by z1 zero. Yeah.
Yeah, so is this correct, by the way? But I mean, is the expression correct?
Yes, sir, it's correct.
Are you sure?
Yes, sir. So one tan inverse will be there. I mean,
Tan
tan
inverse
inverse.
will be added like tan.
Still, it is correct. Is it correct now?
Sir, like P2, if we take, then it would be negative, so we have to account for that.
Correct. So it is basically. Uh, no, no, sorry.
For
Yes,
P2
sir.
it will be negative. Yes.
P2 is in pole, no, so it will be directly added at minus tan inverse omega u loop by P2.
Right. So now, is it correct? I mean, because there are a lot of confusion among you people. So is it correct or not?
Yes, sir,
For
it's
I,
me,
correct.
I
it's
think, sir,
correct.
it is correct.
Okay, cool.
It's correct.
So why were you so confused? I mean, I was trying to confuse this. You were so confused. So one easy way to understand whether you have written the correct signs or not. So basically, if you see that this guy, this pole P2 and omega z, they simply reduce the phase margin, isn't it?
Yes.
So if P2 comes closer, if this P2 comes closer, that is basically if P2 reduces in magnitude, then your phase margin should reduce, right?
Yes, sir.
So is that happening here or not? So that's just a sanity check. So if P2 reduces here, okay, so this tan inverse something, this will increase, right? If P2 reduces, this will increase, isn't
Mm.
it?
Yes.
And this is getting subtracted, so basically overall the phase margin decreases, right?
Yes.
So that is why it is correct. Same holds for omega z also. Okay,
Mm.
cool. So we have phase margin equal to 60 degree, and this is 180 plus sorry, minus 90, so it simply is 90 minus tan inverse of omega u loop by P2 minus tan inverse omega u loop by omega z. And 1 second, let's see. So now I will do something which let's see whether that makes sense or not. Let's assume that omega z is much greater than omega u loop. Okay, I am assuming something. Okay, I'll see whether it makes sense or not. If this assumption is not correct, then we will have to tweak it again. Okay, But for the first ever calculation, when you do the first calculation, okay, you should not take into consideration all the complexity. That will simply become a headache for you to handle. The mathematics will become simply a headache for you to handle. Okay, first of all, when you try to solve something, try to get an estimate, and estimate by making approximations. Okay, when you make approximations and you get some answer, that answer, if it justifies the approximation, then you are good, you are well and good. But if the answer is going to negate that approximation, then you will have to redo that whole calculation without the assumption. Okay, so first let me assume this condition here. If I assume this guy goes right.
Oh, this will be 90.
I
No,
don't
sorry,
think
this
so.
will be 0. Sorry, this will be 0. Sorry, sorry.
Right, right.
Yeah.
Yeah, so my bad. Yeah, so this is 90 degree. So what it will be? In that case, tan inverse of omega u loop by p2 will be equal to what? 30 degrees, right?
Hmm.
So what is the relation between omega u loop and p2? Tan 30 degrees, right?
Hmm.
And what is it? 1 over root 3, right?
Hmm.
Is it? I mean, I'm not sure. Is it 1 over root 3 or
Yeah,
not?
yeah, 1 over root 3. Tan
Yeah,
60
Yes.
root 3, tan 31 over root 3.
correct. So omega u loop from here comes out to be sorry, p2 comes out to be uh, root 3 times omega u loop, correct? And what is p2 location? P2 is equal to what? Approximately.
GM2 into C by C plus 1 plus GO2 divided by
Like, if we
CL.
take everything approximated, then it will be like GM2 by CL.
Correct. So but
Yes, yes, yes.
right, so let's assume that also. But for yeah, so this is basically C divided by C1 plus C, right? Plus GO2 divided by Cl plus series combination of C and C1, right?
Hmm.
But let's assume that C is much greater than C1. Okay, and it is given already that your GM2 is much greater than G02, right? I mean, GM2 value is what? GM2 is 80
Yes, yes.
microsiemens, G02 is only 8.8 microsiemens. That is kind of 100
100
factor of
times
100,
better.
right? So it will become what? GM2 divided by CL, correct? Now tell me, what is it? What is GM2 and what is CL?
GM2 is given and CL will be
CL
now
is given, right?
1040.
CL is given.
1040. CL should be 1040.
Yeah, correct. So, but it doesn't matter. I mean, 1.04 and 1 is approximately close. So let's call it 1 only.
Hmm.
No need to take that into account. Okay. So this will be what?
It will be nearly 80 megahertz.
Correct. So, but this is what? This is not megahertz. Is it
Mega rad per
megahertz?
second.
Radian.
Yeah, correct. This is radian per
Okay.
second.
Okay.
Correct. Is it clear till now?
Yes, yes, it's clear.
Cool. Now what is pole P2 from here? Oh, sorry, pole P2 is given already, right? Now what is omega u loop from this? If pole P2 is known, so how can we calculate omega u loop?
G1 by C.
No, no, no. Omega u loop will be what from this? It is already calculated here, right? It will be P2 by root 3, correct? So it is 18 to 10 power 6 divided by root 3, correct? Radian per second, isn't it?
Hmm.
Yeah. And what is omega u loop in terms of the parameters? So omega u loop is what? Approximately
GM1 by C.
gm1 by cc or c, yeah, right? Sorry. Yeah. So from this one, from these two, you can calculate c, right? So you see c is equal to what? Gm1 by omega u loop. And what is that? Gm1 is what? GM1 is
20 micro.
20
20
micro.
micro.
Correct? Divided by omega u loop is what? 80 into 10 to the power 6 and into root 3, right?
Yes.
So what will it be? This is basically root 3 by 4 into 10 to the power minus 12 farad. So this is root 3 by 4 picofarad. Correct? Is it correct?
Yes, sir.
Okay. Now I made some assumptions, right? While calculating this value of C. I assumed that omega Z is much greater than omega U loop. Also I assumed that C, the first assumption was this one, right? Second assumption was this one. C is much greater than C1. Correct? Now this is the value of C, and what is C1? 10 femtofarad, right? And this
Yes.
is your C. So is this much greater than C1?
Yes.
So
Yes, sir.
basically C is much greater than C1. This assumption is justified, right?
It's picofarad, so it's nearly than 433 femtofarad. Okay.
This assumption is justified, isn't it? Correct? Now let's calculate omega Z. What will it be approximately?
GM2 by C.
Correct? What is GM2? 80 10 to the power minus 6. What is C? Root 3 by 4 into 10 to the power 12, isn't it? Isn't it?
Yes, yes.
Yeah.
Yes.
So what will it be? What will it be? 320 divided by,
Root.
sorry, root 3 into 10 to the power 6 radian per second. And what is the value of omega u loop? What was omega u loop? 80 by root 3 into 10 to the power 6. Okay, yeah. So this was omega u loop, right? Right?
Yes, yes.
Basically radian per second. And this is basically what? Omega z, right? So it is 4 times greater than omega u loop. So is our assumption really justified?
No, sir.
Right. So you'll have to calculate again. You have to go back and you have to add that omega z factor that you were saying. Okay.
So
So
what's the
but
issue here, sir? One more
yeah.
this thing. What's the issue over here?
You see this, we made an assumption here, right? That
Uh-huh.
omega z is much greater than omega u loop.
Yeah.
This
Yeah.
assumption is valid if you get a factor of 10, like, okay, if you have a factor
Okay.
of 10, so but that factor is not there, you have a factor of only 4 here. So but you see, if you do not consider that, you will have some error. So but let's go with exact value. So assumption here that omega c is much greater than omega u loop is not valid, isn't it? Now in that case, the phase margin is what? Again, the phase margin calculation will be, it will be 30 minus, sorry, it will be 90 minus 90 minus tan inverse of omega u loop divided by divided by p2 minus tan inverse of omega u loop by omega z. This is your phase margin, isn't it? So now we will have to calculate it. It will become a messy calculation again after this.
Third out. Just one doubt.
Yeah.
If since it's given that the Obama is not compensated for a phase of 3, is it safe to assume that P2 is actually P2 and Z1 are always beyond omega u?
Yeah, it is.
Because
It is beyond omega u, right? Yeah, right.
okay.
Okay, so basically here you see, if you do not assume this, if you assume this and then you get an answer here, omega u loop is equal to something, omega z is equal to something, capacitor c is equal to something here. Okay, and you see that basically is it comes within the required range. So what is this value, by the way? Root 3 by 4 picofarad, what is it?
It is nearly some 433.
420.
And what is the range in which the answer is expected?
640
820.
to 830.
Yeah, so basically this is not correct in that case. You'll have to assume, you'll have to see whether this basically you'll have to take into consideration effect of omega z. Okay.
Sir, omega u loop equals to gm1 by c, no sir. Omega z equals to gm2 by c.
Yeah.
So it comes to be gm1 by gm2, sir. Tan inverse of. So it will be tan inverse of 80 by 20. 20 by 80, tan inverse of 1 by 4, that is approximately 16 degrees.
Okay, so let's do that. You want me to calculate it, right? Okay, so this is basically omega u loop by p2 minus tan inverse of, right, so as he said, gm1 by gm2. Okay, and this is what 90 minus this is what is this? Basically 20 by
14.
80, 1 by 4, right?
4.
Right.
Yes.
Yes.
And what is that?
14 degree.
14 degrees, sir.
14 degree.
Yes.
14 degree you said.
Not 14, it's 15.9, that's 16 degree nearly total. All over the calculation.
No, tell me what is the value of
No,
this?
no, no, 14, 14, on 4, sir.
Okay, that one.
14.03.
Tan inverse of omega u loop by p2. So this has to be equal to 60 degree, right? So this is what, 30 and minus 14, and that is equal to 16 degrees. Yeah, and that has to be tan inverse of omega u loop by p2. So from this, what will you get? P2 is equal to, or omega u loop is equal to P2 times tan of 16, right? What is that? I mean, from here you can calculate, right? I mean,
But
Yes, yes.
yeah.
Yes, sir.
I mean, is this the doubt? I mean, what was the doubt? From here you can calculate, right?
no, the doubt is like now if for the equation of omega u, if you are putting gm1 by c, and in that p2 also if you are putting that approximation of gm2 by cl, now the answer will also come nearly some 900 femtofarad. But the answer is some 640 to 840. So the
So basically,
approximation.
the is not valid. Approximation, according to the condition, it is valid. C is much greater than C1, but the answer range which they have calculated is only valid, is only right when we calculate using the exact equation.
Yeah. So
Otherwise, the answer is not
yeah. So
coming.
by the
Sir,
way, I will have to ask you: is this range given in the when you attempt the assignment? Is this range given to you
No, sir,
No,
not
beforehand?
no, no.
This range is not
No.
no,
given to you.
No.
no.
No, sir. What my mistake I understood actually now only these
Hmm.
are the in approach wise I understood that approach was it was correct. Why what my mistake for that reason many of the questions were wrong. Actually, I calculated in that radian per second. It was evaluated in radian per second, but I put that answer in hertz only. I forgot it to convert it into hertz. So that was the main problem. I think now if we are putting the P2 and omega you look the more or less the exact equations, I think their range will match.
Yeah, so we check that, okay, but the procedure is that this, okay. So
Sir.
whenever you assume something, we'll have to check whether that assumption is indeed valid or not. So is that clear, right?
Yes, sir.
I mean,
Sir,
yeah.
so how
Yes.
do we inform the NPTEL administration about this wrong answers, which is or because of the wrong range, basically, whatever is happening? Like this is continuously happening for the past 3 weeks, and we are continuously losing our marks on these assignments.
Okay, so don't they have a? You can contact the instructor, okay? You can mail him.
So we have to mail Professor S. Aniruddhan.
Yeah, you can mail him.
Okay,
Okay.
okay,
Yeah. Okay.
thank you.
Yeah. Welcome. So reiterating it, I'm reiterating it. The fact that when you start calculating when you start attempting a question, do not try to write exact expressions just for the first time. Okay, when you start attempting something, go with try to make the complexity as less as possible. Okay, assume everything to be basically you make approximations. Okay, and calculate based on those approximations, and after that the values that you will be getting, try to check one by one whether those values justify the approximation or not. If they do not justify, in that case you'll have to go back and do the calculation without the assumption. If they justify, then you're good, right?
But still, sir,
Yeah,
for that approximations we use a c greater than equal to greater very very much greater than c1.
yeah.
Like up to how much?
No,
Like if the
if the
result
if
is
the if the value is greater than 10, it's okay. I mean, 10 times is good enough.
okay, so something 10 and 200, so I can approximate it like 200 only.
Yeah,
10 plus 100, yeah.
yeah, yeah,
Okay,
definitely, yes. I mean,
okay,
that
sir.
gives an error of if you take a factor of 10, that gives more or less an error of 10%. Okay,
Yeah,
that's
yeah.
tolerable
Actually,
generally.
sir, from the marks point of view, I'm asking this question only because as long as the approach is correct, I'm okay with that. But also here, the marks is oriented in this. For that reason, I'm asking these questions. Otherwise, approach is okay, then I'm okay.
Yeah, so you can mail Professor Aniruddhan about this.
Yeah, yeah.
Okay.
Thank you, sir.
Yeah, welcome. So I guess this clears the problem, right? So I have to delve into this another thing that I want to discuss today. So I want to discuss this intuition of this poles and zeros. Okay, so let's deal with this. Uh, yeah. Or I'll come back to it later. First, let me discuss something about this week's assignment. So I guess a lot of people don't know how to attempt this week's question. So let's first do that. Uh, yeah. So this is the this week's question, right?
Yes, sir.
Correct.
Yes.
So let's go into this. So do you people know what is how to model this, by the way, in terms of offset voltage and the input offset currents? How to model them? Yeah. So do you guys know?
Offset voltage, I think in lecture it was discussed, but input bias current it is input offset.
Yeah.
Those
So
are not
let's.
discussed.
So bias currents can be modeled, I think, with a resistor between the input and between the both the input pins.
Yeah. So that's not actually correct. So you do not want to worry about what is there inside. Okay. What happens is that you see the nowadays this input offset current is not much of a problem because we use MOSFETs. Okay, we use MOSFETs, something of this kind. So this this op amp here, the input will be something of this kind, a current source here, and this will be something of this kind. This will be one input VN, or let's say this is VP and this is VN. Okay, it will be something of this kind. And MOSFETs, as you know, they do not take any current inside. I mean, to a first order approximation, because MOSFETs are what? Their input is basically, they are something of this kind, right?
Capacitor.
So they have you have this oxide here, you have gate here, you have this gate here, and this is basically your drain, and this is your source, and this is your bulk, which is basically PMOS. No, sorry, this is your body. Okay, so in between gate and so basically this is the gate here, this is source and drain. So there is no direct connection between gate, source and drain. Okay, there are basically in between these there is this oxide layer present here. Okay, this oxide is basically an insulator. Okay, so there can be no current passing through here directly. So the current here, you can assume that current here is simply approximately equal to 0. Okay, that is when you implement this using MOSFETs. Okay, so this MOSFETs here, the input current, the current going through the gate is approximately equal to 0, more or less you can say. However, this being said, this is not actually true for modern CMOS processes. So, are you understanding what I'm saying right now? Anyone?
Yes, sir. Yes.
Yeah. So
Yes.
basically, modern CMOS process, they basically, like you must have heard, right? 3 nanometer process or 45 nanometer process, something like that,
Yes.
right? So those lengths or those sizes, this approximation is not actually valid. There you have the current, actually you have this current, leakage current. We call it leakage current, IL, and this also IL. Okay, so in that scenario you have these currents. But if you talk about large length processes like 180 nanometer or 250 nanometer, something like that, in that case you can say approximately that the current going inside here, the input bias current or input offset current, they are actually zero. Okay, when you implement this op amps using MOSFETs. But when you implement this op amps using this BJTs, then that's not the case. You remember, right? Because BJT, you have some base current, isn't it?
Yes, sir.
You have
Yes.
some base current, you have some collector current, you have some emitter current. And what is the relation between collector current and base current?
IC is equal to beta
Big.
I.
Right. So basically, you have to have some base current here. Only then can you have some collector current. So this input offset current problem is actually a more severe problem for BJT based op amps or BJT based electronic devices. Okay, it's not such an issue. It's not such a big issue with MOSFET based electronic devices. Okay, so that was just a motivation here. So let's remove this. Yeah, so now let's come to this question. So you have been given that you have MOSFET, you have this offset voltage here. Okay, you also have what, input offset current, right? So how do you
Yes.
model these? How do you model these? Yeah, how do you model this?
Sir, we add current source from one terminal.
Correct. So basically you assume that you have a current like this, and let's assume that this goes into something. Okay, let's not worry about this, and this is like this. This goes into something we do not know about. Okay, so don't worry about that. You can assume some resistor here, doesn't matter. You assume that it is going into something here. Okay, now after that we have this, and this here is called Vi, right? This is VO. And what is the offset? How can you model offset? This is basically current. Okay, this is IN IP, let's say this is IN. Okay, these two are the offset current, these two are the input currents. Okay, this IP and IN are the input bias currents, you can say. Okay, and how do you model offset voltage, this input offset voltage here? How do you model it? Come on, man, this was also taught to you in the class and in the lectures.
The bio voltage
Voltage
Sir, in the
source.
same manner, we can add a voltage source.
Yeah, so where do we add it? Here or here?
Positive. Positive terminal.
You can add it anywhere, okay? It doesn't matter.
Sir, we can add any terminal,
Yeah.
but
So
generally positive.
correct. So let's add it here. Okay. Now this is V offset. Okay. Cool. Sorry. Yeah. So that is done, right? Now let's. So okay. Now this whole thing, uh, everything which is inside this box here is not accessible to you. Okay. You cannot access this. They are just inside. You cannot do anything about it. What is accessible to you are these terminals here. Okay. This is one terminal. This is another terminal here. This is another terminal here. Only these three are accessible to you. This is VP, this is VN, and this is your V out. Right? Only these three terminals are accessible to you. You also have some power supply here, but let's forget about that. So these three terminals are only accessible to you. Okay. So now you want to measure, but yeah. So you understand that these three things, IP, IN, and V offset, these three things are non-idealities, right? You should not ideally have them, isn't it?
Yes.
I mean, ideally, IP should be what? IP and IN should be what?
0.
Right, 0.
Zero.
And V off should also be equal to 0. You do not want anything in between, right? So these things are a non-ideality, and you want to ideally you will be happy when you do not have these things. But in real op amps, these are there. You cannot do anything about it. Okay. So what is the next best thing that you can do? Yeah. Anyone? I mean, these things are present here. Okay. You cannot do anything about it. So what should you do? You have a problem.
Minimizing that.
Nullify them externally.
Correct. So somehow we will have to do that. But how will we nullify that? So first, the first thing is about first principle of engineering is what? You have some problem. You have to identify it, right? You have to identify and you have to quantify what is the problem and how much is the problem, isn't it? That is the first principle of engineering. You solve problems, but before solving them, you have to first find out what is the problem and how much is the problem, isn't it? So for that, so what do we mean by that is that you have to calculate how much is the V offset. Suppose you are given an op amp to you, you go to market and you buy an op amp, okay, and you get an op amp. It will come with its own set of non-idealities, right? So first of all, you'll have to find out how much is the non-ideality in this particular op amp. So you'll have to do some set of experiments to measure how much is this offset voltage V off, how much is this offset current IP and IN, isn't it? Yeah. So for that, this is basically the experiment here. What do? We calculate each of for calculating these three. You require three equations, right? That makes sense, right? You have three unknowns. You require at least three equations.
Yes, sir.
Yes, sir.
Yes, sir.
So you do three sets of experiments, okay, and then from these three sets of experiments, you will get three equations. And from these three equations, then you can find out what is the value of V off, IP, and IN, isn't it?
Yes.
Yes.
So that is what is done here. You have three experiments here, okay. So let's see. So what is experiment number 1? Experiment number 1 is what? Yeah, come on guys, tell me. What is experiment number 1? Have you gone through this week's assignment or not?
Yes.
Yeah, so you see the experiment number 1 is basically you put this, sorry, and you have this resistor here, you ground it. Okay, and now let's model this offset here like this, V offset. And by the way, this Vs here is assumed to be 0, you ground it. Okay, so as I said, this this V offset is a part of op amp itself, right? You cannot do anything about it, isn't it?
Yes.
This is a part of op amp itself and you cannot do anything about it. So what is accessible to you is the thing which is out of this, the terminal which is outside of this, isn't it? So this is the terminal that is accessible to you. You can add anything here. So this was Vs, by the way. Okay, but now let me ask you, if you have to calculate V offset, if you have to find the effect of offset voltage, how will you do it? What is the what does your intuition say? What does your common sense say?
Short circuit the input.
Correct. So basically this here, this terminal here which is hanging, just ground it, right? Because you do not want to have you want to see the response of this op amp only because of the offset voltage, isn't it?
Yes, sir.
Yes, sir.
Correct. So what do? We simply nullify this input voltage Vs here. We make it 0, right? Short it basically. Correct. So after that, this is the situation that you have. This is the condition that you have. You have this V offset, and anything that will appear at the output will be because of this V offset, right?
Correct.
If the V offset was not here, yeah, if the V offset would not have been here, what would happen? If V offset was not there and you nullified this input voltage here, what will be the output voltage here?
0.
0. Correct. But because of this V offset here, you now cannot have 0 voltage here, right? You'll have some some output voltage,
Yes.
right?
Yes.
Yes. So in order to find the effect of V offset, this offset voltage here, what do? First thing is that we have to nullify the input voltage. Okay, all the inputs that you have in the system, you just nullify them, except the power supply, of course. Okay, and after that you check what is the output voltage. Okay, so experiment 1 is nullify all the inputs and measure the output of the op amp. Okay, fine. So this is what is done here. See, op amp, yeah, the output VO is monitored with a voltmeter and is found to be 0.480 volt. Okay, in this non-inverting amplifier of figure 1, which is this particular amplifier here, let R1 is equal to 10 ohm, this is 10 ohm, this is 10 kilo ohm. Okay, mind it, this is 10 ohm and this is 10 kilo ohm. Okay, so and Vs is equal to 0. So basically they have nullified the input, right? This was an externally applied input and they have nullified it. Vs is equal to 0, so that is why it is nullified. Fine. After that, the output VO is monitored and with a voltmeter and is found to be 0.480 volt. So this voltage, after doing all that nullifying, it is found to be equal to 0.480 volt. Okay, fine. Now if the situation would have been if there would have been no input currents, then basically you can directly say what is the output voltage, what is the offset voltage. Let's say this is current is 0, this currents are 0, so what is the relation between V off and V out?
1 plus RL by R1.
So V out will be equal to 1 plus
R2 by R1
into
V in.
offset. Correct.
Yes.
But this happens if I is if
0.
this, let's write it more clearly. This is I1. Okay, this is I2. Let's write it in different color so that it is easier, it is more visible. So this is I1, this is I2. Okay, so if I1 is equal to I2 equal to 0, right? Then you can directly calculate V offset from here, right? But that is not the situation anymore, isn't it?
Yes.
You have some I1, you have some I2. So in order to find these two, so if you have I1, I2, then you will have some extra stuff here, okay? If basically in presence of I1 and I2, V out is equal to 1 plus R2 by R1 times V offset plus some function of I1 and I2, okay? Or let's make it I1 comma I2. Okay, so you cannot directly find out V offset from this equation anymore, okay? So now you need two more equations to find out how I1 and I2 affect the overall system, right? So now what does your logic say? How will you, means you have to find out what is the effect of I1, right? I1 and I2 on the output. You have to calculate what is I1 and I2. So for that you have to basically change something at the input terminals to make sure that the output is affected by the current, isn't it? And that effect can also be understood by you. So what does your logic say? How can you design such an experiment? What will you do to make sure that you can study the effect of I1 and I2? What should you do? You see, I1 and I2 are there in the system, okay? You cannot do anything about it.
Like, can we do superpositions? Like,
Yeah, we can do superposition, but how will you do superposition? I mean, you'll have to find out V out, right? Always, the only three things that you can observe is the input, which is the two input terminals that are this VP VN, okay, VP VN, and only the output. Only these three terminals you can observe and tweak at any point of time. Now, what should you do to make sure that you can like basically in order to observe V offset, this offset voltage, what did you do? You said that okay, we will simply short the input, and because of that when you short the input, any output that we will be getting here will be because of V offset, right? That is true, exactly true. But now because the system also has this input currents, the output V out will not only be dependent upon this V offset but also be dependent upon this I1 and I2, okay?
Yes.
So what I am
Sir,
asking is, yeah, go on.
sir, we can make RO1 infinity. So in
RO1
that
infinity. Yeah, so I like your approach, basically RO1 infinity. So basically, also what is RO1 by the way? Are you talking about this one, two stage mirror compensation? Then
That are R1. I mean the RO1 and R2.
this is R2 and R1.
These are R1. We can make it in infinity. So
Yeah, so I like your approach. So basically you are saying that if you tweak this R1 and R2, the current that is going to flow here will also be means basically that will change the voltage obtained around here, right? Across it. That is what you're saying. I mean, that is what your thinking is, at least.
Yes, sir.
yes,
Yes, sir. Yes, sir.
Yeah, so that is correct. So what do we do actually is we go to the second experiment now. Second experiment is
Starting 1 megavolts.
yeah. Second experiment is what? What do? We take this op amp here. Sorry, not so good with drawing. And what do? We this is the same thing. This again here is the same thing. But now what do is that we also attach a resistor here, okay? This was the terminal, okay, that was accessible to you. We attach a resistor here, a very big resistor. Let's call it R test, RT, okay? This is R2, this is R1, and this was the same thing. I mean, this is the same old. You simply ground it, null it. So when you null it, the only thing, the response will be simply because of this V offset, right? So I'm again saying that this V offset is not actually what we are applying externally. This is a part of the system itself. I'm just modeling it here. This is just a modeled entity. This is just model voltage source and not an actual voltage. Okay, fine. So what do? We add a very large resistor here. So let's again make it different color. This is RT. Okay, and now you see you have the currents also, right? You have the current here. Let's So this is the current I1, isn't it? Is that clear?
Yes. Yes.
Right. And this is the current I2. Okay. But now this I1 current will also introduce a voltage difference between across these two terminals, right? And now
Yes.
basically what is the effect of I1 can be understood by you. I mean, you can quantify, you can say something about the effect of I1, right? But still you are not able to know what is what is the effect of I2. I mean, if you apply a voltage source across any terminal, okay, so this is basically a voltage source, right? And you apply it here across some terminal, the voltage here will be V offset only, irrespective of what current is flowing through here, right? So you cannot say anything about I2 here till now. So what should we do? I mean, for I1 we did something, right? So what should we do for I2 now?
Again, we can connect the resistor.
Correct, exactly. So this is the exact thing which we will do. So the third experiment is basically yeah. So by the way, in this experiment, you observe V out. Okay. Now experiment 3 is this one. Take this op amp here. Okay, and this is R1, this is R2, this is minus, this is plus, and now instead of connecting it in the inverting inverting terminal, you connect it here. Okay, this is RT, and you again have that modeled voltage source here, V offset. Is that clear?
Yes.
Sir,
Yeah.
sir, we are adding the RT externally, right?
Yeah, we are adding RT externally. Yes.
Okay,
Okay.
okay, okay.
Sorry. So yeah, I understand your confusion.
Yes, yes, sir. Yes, I am.
So this is V offset, and this is the terminal that is accessible to you. So you add RT here. Okay. Cool.
Yes, sir. Yes.
Yeah, understood. So yeah. So after this, what do? We again observe this RT and this RT here. They are same. Okay. It doesn't matter. You can also add two different registers. It will simply complicate your life when you finally calculate. But it's okay. I mean, as long as you know what is the value of this resistors. So after this, you observe V out. So basically, you will have three equations. Okay. Now, three equations will come out for V out. And how will you find three equations? In all the three, you will have the effect of all the three non-idealities. Okay. In all the three experiments, you will have the effect of V offset, I2 and I1 in all the three. Okay. But it's just that when you try to, when you are changing some things, right? And when you change some things here and there, you are basically modifying your circuit in order to ensure that the effect of one is different from the effect of other, so that you have three different equations to deal with. Okay, are you understanding the logic here? In all the three, you will have the effect of I1, I2 and V offset in all the three experiments, but it's just that when you change the value, when you add resistors or when you modify the circuit in some manner, you are making sure that the effect of one non-ideality is different from the effect of another non-ideality in each and every experiment, so that you have got three different equations overall, and when you have these three different equations, you can solve them and you will get the final value of r1 r2 and i1 i2 and v offset. And how will you find the three equations? In here, what is the value of v out in terms of what is v out in here in the first experiment? You'll have to do what? Here you can assume that AB gain is infinity. Okay, you can assume that the gain of the op amp A is infinity for this particular assignment, this particular problem. Okay, you can assume the gain to be infinity. So I'm asking, what will be the how will you find out V out here in terms
So
of I1 I2 and V offset?
virtual short is valid.
Yeah, virtual
So
short is indeed valid. So see, if the gain A is infinity here, you cannot have this Vi has to be equal to 0. It cannot be a finite value, isn't it?
yes,
So whatever voltage you have here at this terminal, the same voltage you will have to have at this terminal, isn't it?
yes.
So let me just write you the first equation so that you get an idea. So you simply do what? You yeah. So you have I1, I2 and everything, right? So you see that at this terminal we have a voltage source, right? So what is the voltage here? V offset, right?
Yes.
And because of the virtual short, what will be the voltage here?
V also.
V offset. Okay. So now you can write the KCL at this node, right?
Yes.
So what will be the
Yes, sir.
KCL at this node? KCL at non-inverting terminal. Sorry, inverting terminal. What will it be? It will be what?
V offset
Yeah, go on.
plus V offset minus V out by R2
V out
plus
by V out minus. Okay, so I will write. Okay, V out minus V off. Basically, this current should be equal to this current plus this current, right?
yes
So V
Yes,
out
sir.
minus V off divided by R2 has to be equal to V off
by R1
by
plus
R1 plus I1, correct? Right? So this is the first KCL equation. Similarly, you will get one KCL equation here and one KCL equation here. And this V out is equal to V out 1, right? So this is the V out of first experiment. Similarly, the V out that you will get here, that will be V out 2, correct? And the V out that you will get here will be V out 3. So similarly, you will get three different equations for V out. Okay, and all the V outs are different, right? You see, first V out is 0.480 volt, second is 7.780 volt, third is 0.230 volt. So you'll have three different V outs. So and you'll have three different equations for V out. So you can find out what is I1, V off, and I2. Okay, did you understand?
Yes, sir.
Cool. So that's it. Let's see whether you have any doubt here. So I don't think you have any doubt. I don't think there is any clarification which is needed for the second question. Second question is basically the same old, so you do not need any clarification here. So attempt the second question, okay, yourself. Okay, coming back to the thing that I wanted to discuss. So uh, let's talk about poles and zeros. Okay, so let's take any transfer function. Okay, let's take some h of s, which is equal to some k, which is DC gain, multiplied by 1 plus s over z1 to 1 plus s over z2, so on, divided by 1 plus s over p1 1 plus s over p2, so on. Okay, so hold on, wait for a second. Yeah, so this is a general let's say general transfer function. Okay, cool. So you remember, right? If so what happens, what are the constraints on these poles in order to make, in order to ensure that the system is stable?
Pole must be negative. All the poles.
No, no, be more precise. I mean, what is negative? It should be in the negative half plane of the negative half plane of the s plane, right?
Yes.
Yes, yes.
Yeah, system to be stable, all poles must be in the negative half of the s plane, right? Correct. So if you have this s plane here, this is sigma, this is j omega, so all the poles must lie in this region, right? Correct. So is there any constraint on zeros for stability?
No, sir.
Are you sure?
So for like inside UGB, then a number of poles
No,
minus
no, no,
number
no,
of
no, no,
zeros
no,
should
no,
be 1.
no, 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 no. I'm this h of s, this transfer function. I'm not saying this is in closed loop or anything. This is, the system is like this. Let's say this is your input v in. Let's say this is x. Okay, is going through a transfer function h of s, and this is y. Okay, so there is no loop anything here. This is basically a transfer function between input and output. So indeed there is no constraint on zeros, right? There is no constraint on zeros for the system to be for the stability of the system, at least. Okay, the only constraint is on poles, and this will be fairly easy to see if you convert it in time domain. Okay, so from in the time domain, only the poles 1 over s by some p, only these kind of only the denominators, they lead to a exponential this thing, right? When you take inverse Laplace. Do you know about inverse Laplace? Laplace transform, inverse Laplace transforms?
Yes,
Yeah.
it's
Yes, sir.
So only these kind, only the denominators, only those the denominators are present in the exponential. Okay, isn't it? Only the
Yes, sir.
denominators are present in the
Yes, sir.
exponential. No, there is nothing to do with the numerator. So numerator will not be present here. Only the denominators are present here. Okay. So if the denominator here is this p becomes negative somehow, then basically you see that 1 minus pt, sorry, e to the power minus pt will become positive, isn't it? If p is less than 0, then this guy will simply exponentially rise, right? So that the system becomes unstable. Okay, so basically you only have the constraint on poles and not on zeros. So
Sir,
yeah.
so one question, but if we have a feedback or if we have a loop,
Uh-huh.
then will we have a constant on zero also? By that,
What?
I mean, if we have a loop, then
Uh-huh.
we will have a constant on zeros also.
Why not?
Okay. I mean, you deliberately said कि in without loop there is no constant on zeros. So
Oh,
then
okay, 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 okay. Oh, I didn't get your question. So yeah. So basically, if you do not have a loop, no, no. My question is my. Okay, so I am not able to deliver my point properly. So you see, there is a misunderstanding here. What I'm saying is, I have a simple transfer function between some input and output. Okay. So if you have this particular situation here, if you have a loop, okay, this is g, this is h, right? Still, this box inside can be replaced by an equivalent block, right? This is x, this is some equivalent, what do you say, h prime of s, and then this is y, isn't it? You can replace it in this manner.
Yes.
So what I'm saying, let's say you have this box here, you have between input and output, you have this transfer function h prime of s, and this that h prime of s looks like this. In that case, what is the constraint on poles to make the system stable? That is what I was saying, nothing else.
Okay. So, because in lecture also we have seen zero have some constant, but
Yeah, so
by
that
by
that
that,
that will come, yes. I mean,
yeah.
that will come when you are looking only at this h and this g. Okay, when this loop, I'm not talking about loop gain right now. Okay, I'm just talking about, I'm replacing this whole this box stuff here with a simple equivalent block.
Okay, sir.
Okay, so this is the closed loop transfer function, by the way, h prime of s. This is a closed loop transfer function.
Okay, sir. Got
Yeah,
it.
so let's come back to what I was saying. Now, this pose and these zeros do not make the system, sorry, this pose should be in the negative half plane to make sure the system is stable. Okay, cool. Now, in the lectures we saw, right, when we have a loop, this is x, this is negative feedback, let's say this is omega u over s, and this here we had a resistor divider, right, k minus 1 times r, and this was r, and this was v out, so this was v in. Okay, so when we had this system, this basically was the ideal system, right? This was the ideal system. Now we also saw what happens when we add a loop, when we add a pole in the system, extra pole. So basically if you have this s into s plus p, so what happens? Yeah, so what happens when you add an extra pole here? Come on, quick. What happens when you add an extra pole here?
Some
Actually, it's reaching some reaching to positive feedback, which due to the
Delay is
delay.
added.
Delay
Yeah,
will
so
be added
basically
to
what is this pole doing? This pole is
delay.
adding some delay, right? This is what you understood.
Yes, sir. Yes.
This pole is adding some delay. And how is the pole adding a delay, by the way? How does a pole add a delay?
It's lag because of the phase lag.
Yeah, so let's
Time delay because of phase lag.
see this. Uh, V out, and this is V in. This is R, this is C. So what is V out by V in terms in this domain,
1 by 1 plus
1
x.
by 1 plus s.
right? Right? So in
Yes, sir.
this case, what is the pole location,
1 by RC.
right? Fine. So what do you see in this case when you apply an input here in the step input? How is the response to the step input at the output?
Time dominates exponential.
Correct. So let's say this is your step input.
Exponential charging. Exponential charging.
Yeah, so this is input. So step output is what? This is like this, right? Correct? So you can see clearly that there is some delay. It is not an ideal delay. What is an ideal delay? What would be an ideal delay? If the system's response goes like this, right? After some time, this is, if this is TD, then basically the output will look something of this kind. V out would look something of this kind. That then you can say that the system has an ideal delay, right? But this is not an ideal delay. This is some kind of delay, but this is not ideal. This is not the usual delay that you are used to see. This is some kind of delay, but it is not ideal. It is delaying when you see it after a very long time, right? I mean, after a very long time, if you see this, observe this output, then you can say that, okay, so this system is looking something of this kind. So maybe it would have started, I mean, you can model it in after a long time, you can model it in this way. that the system's output was like this. You can say you can say this, right? I mean, to as an approximation. Is that clear?
Yes, sir.
Right. So this is not an ideal delay. This is some kind of delay. So a pole adds some delay to the system. A pole actually adds a phase delay. Okay. It is not a time delay. It's a phase delay. A pole actually adds a phase delay to the system. Okay. So basically, when you apply input here of cos omega t, what will you see at the output? We'll have this magnitude. The output V out will be what? 1 over 1 plus omega square r square c square under root, and this will be omega t minus tan inverse of rc. Okay, this is what you will see. And if the rc time constant, so basically this is a phase delay, right? Are you with me or not? Are you understanding this
Yes, sir.
part or not?
Yes, sir.
Yeah,
Yes,
yeah.
sir.
So okay, so I require some feedback from you, otherwise I don't know whether you are understanding or not. So this is a phase delay, right? This is a phase. This is a phase, right? Anything which is inside the, okay, so this is cos, by the way. So anything which is inside this is in the argument of cos is phase, right? Omega t is also phase. This is also phase. So you can see that there is a constant phase offset between the input. Input was what? V in was cos of omega t, but output is delayed, right? By tan inverse of omega c. Yeah. So fine. So this is the phase delay which pole adds to the system. Cool. And this phase delay we can model it in terms of time delay also. We can say something like that. Like if RC is much less compared to, oh, so sorry, here there is an omega term also. Omega RC. Okay. You also have an omega here. I forgot. So if RC is much less than, or not RC, if 1 over RC is much less than omega, then can you simplify this? Then this tan inverse of omega RC, it can be written as tan inverse of, it can also be written as tan inverse of omega by 1 over RC, isn't it? It can be written like that.
Yes, sir.
Sorry. If RC is much greater than, so yeah, so if RC is 1 over RC is much greater than omega, and you can write tan inverse in this manner also. So can you simplify it further if this approximation is given here?
It will be 0.
Yeah, it is 0, but yeah, that is like a very crude approximation. So I'm saying a slightly refined approximation that. So you know that
Oh,
if
omega.
sine of theta, what is it approximately equal to if theta is much less than 1? Theta, right?
Theta.
Similarly, tan theta is approximately equal to theta when theta is much less than 1, isn't it? So here
Yes.
also omega divided by 1 over RC is much less than 1, right? Omega into
Yes.
right. So this can be approximately written as what? Omega divided by 1 over RC, isn't it?
Yes.
Correct? Right now? Cool.
Yes, sir.
So if you
Yes,
do
sir.
this and you have this V out, right? So V out was what? It was 1 over root over 1 plus omega square r square c square into tan inverse, sorry, not tan inverse, but cos of, it was omega t minus tan inverse of omega rc, right? And now in this approximation, what can you say? It can be written as V out is equal to, approximately equal to, if omega rc is much less than 1, right? You can say that this is equal to approximately 1 over 1 plus omega square r square c square cos of, and this is omega t minus, this can be simply taken out of tan inverse, right? This is omega rc, correct?
Yes, sir.
So now you see that it can be now you see that this term inside the brackets, you can take omega common, and then this is t minus rc, right?
Yes, sir.
Correct? So now you can clearly see that this now becomes a delay, right? So this is omega into t minus something. So this is like delayed, right? This RC can be written as some TD delay, right? You can see that clearly for omega. This clearly now looks like a delay, right? So a pole in the system, it can behave like a delay. It behaves like a delay when the pole frequency is much lesser than the frequency at which you are giving the input. Okay, then you can model it in terms of the delay. You can say that the system is delayed by that much of time. Okay, cool. So this was about this is when we have a left half plane pole, right? All this approximation, in this case you see this pole is where is in the negative plane, right?
Yes, sir.
Yeah. So this is why in your lectures also you learned that when you have when we have some poles in the system, in the overall feedback system, when we have poles in the overall feedback system, then it can be modeled as some delay. Basically it acts like a delay in the feedback system, and that is why when you have a delay, and you know that when you have a delay in the feedback system, the system has a tendency to become unstable, right? Correct. So that is why
Yes.
the poles, the extra poles that you add in the system are going to cause a problem of instability in the system, right? That is what you saw actually. Okay, cool. Now you also saw that a right half plane 0, right? So this let's talk about right half plane 0. Yeah. So you remember this let's forget about GO1 here. Okay, this GM1. Okay, so you remember, right, that in this case we have a right half plane 0, isn't it? And what is the location of 0?
GM2 by C.
GM2 by C, correct.
Sir, I have one question, sir.
Yeah,
Sir, by intuition, can we say the location of zero that is in right half plane or left half plane?
so that is what
Or
I'm
we have,
coming. That is what I'm coming to.
okay, okay, okay.
Yeah. So you say that you remember that the location of 0 here, 0 is GM2 by C, and it is in the right half plane, right? It's in the right half plane, correct?
Yes, sir.
Cool. And you also remember that this 0 right half plane 0, in the loop gain expression it was looking something of this kind, 1 minus s over omega z, right? This is how it was looking. So that is why, and divided by 1 plus s over p1 into 1 plus s over p2, something of this kind, right? This was the loop gain expression, right?
Yes, sir.
And you remember that because of this right half plane 0, your phase margin was decreasing, right?
Yes.
Yes.
And what do you think, if the phase margin is decreasing, what can you say about the delay in the overall feedback loop? I mean, if the what happens to the delay in the feedback loop if the phase margin is decreasing, it's going down?
The delay is increased.
Correct. So somehow you can say that somehow the system has had larger delay. Means somehow the system is having larger delay because of this right half plane 0, right? Is that clear?
Yes.
Cool. So now we'll try to understand how does this right half plane 0 actually cause more delay in the system. And we will try to understand it from in the time domain. In the frequency domain, it is fairly easy to see, right? You can see that because of this 1 minus s over omega z, this the phase will be what? Minus tan inverse, right? It will be minus tan inverse omega u loop divided by omega z, right? So you see that there is a minus tan inverse here, isn't it? And this minus sign here, it simply means that it is simply reduced. It is adding extra phase delay to the system, right? If instead of this minus sign here, it would have been plus sign here, then this would have been plus tan inverse, right? And that would have aided in basically that would have aided its stability. I mean, if this would have been this plus sign, then this would have been plus tan inverse omega u loop by omega z, And what does this mean? If the it is simply adding extra phase to the system, it is giving a phase advance or time advance as compared to the negative sign where it is adding extra phase lag or adding extra delay, right? So now let's understand how does it add delay and try to understand it in time domain. Okay, like here we understood, right? We understand that extra pole here, there is a pole in the system, right? And when you can clearly see the effect of this pole when you apply a unit step, right? When you apply an input as unit step, you can clearly see that the output takes some time to settle, right?
Yes.
From this you can understand that the pole is adding some delay. So now let's do a similar kind of experiment and try to understand how a right half plane 0 introduces delay. Okay, cool. So now so now you remember that the 0 was introduced because of these two paths adding together, right? In different phase, correct?
Yes, sir.
Yeah. So as far as 0 is concerned, we can get rid of the part which is before that, right? I mean, we can get rid of this right here. We can get rid of this as far as 0 is concerned. Okay? 0 is only coming because of this guy here, right? Okay. I mean, is that clear? 0 is coming only because of this second part, right?
Yes, sir.
Yeah. So,
Yes, sir. Yes, sir. Yes.
yeah, cool. So keep saying something, okay? Otherwise, I do not know whether you are understanding or not. Cool. So let's understand now. Intuition behind RHP 0 adding delay to the system time domain intuition. Okay, so we have this condition here. I'm only looking at the second half of the basically GM2 and this C, and I'm not looking at everything else. This is CL, this is G02. Okay, this was minus, this was plus. So now tell me something. When you apply a unit step, okay, so how do we quantify whether the system is adding delay or not? We simply add a unit step, right? U of t, and we'll see how the behavior of this output looks like, isn't it? Here
Yes,
also
sir.
we added a unit step here, and we saw how the output looks like, right? Because the output was delayed, because output was slowly rising, so we could say that the system is delayed, right? Here also we will apply an input here, which is a unit step, and see how the output looks like. So what do you think the output will look like here? Yeah, someone. So this is your input.
Sir, instantaneous charging at t equals to 0.
Yeah, what will happen? Tell me.
And then
Yeah, so what will happen? Tell now. What will happen at t is equal to 0?
the output will be v in by 2, like half of the v in.
At t is equal to 0, V out should be what?
Sir, v in by 2.
How come?
No, it should be C into V in by C plus CL.
Yeah, C into V in divided by C plus CL. Correct?
That is equals to,
No. If C is equal to CL, then you are
yes.
right. But C is not equal to CL, right?
Yes, sir. I am talking about.
Yeah.
Yes.
Cool. So at time t is equal to 0, this is the condition, right? So let's say this is here somewhere. C times, so this is V in. So let's say V in is equal to 1 here. Okay. You are adding a unit step of magnitude 1 volt. Okay. So this is C divided by C plus CL. This is somewhere here, right? Okay. So at t is equal to 0, what happens? Your V out, it goes like this, right? And now it will start to decay. And what is the steady state value? I mean, at time t is equal to infinity, what should be the value of output V out?
The GM2 by GO2.
Chat zero.
What?
Zero.
How come? Why? Why should it be 0? This capacitor opens, right, at t equal to infinity. This capacitor also opens, and you have some input here, V in. So output will be something, right? What will it be?
GM2 V in by G02.
GM2 V in by G02.
G02, yes.
Is it correct?
Yes, sir.
I don't think so.
Yes, sir.
It is not correct.
Yes.
It is there will be a minus sign here, isn't it?
Okay, okay, yes.
Yes,
There
sir.
is a minus sign here, so there will be a minus sign here also. Cool. So at t is equal to infinity, it will discharge in some fashion and it will become something of this kind, right? Is that
Yes.
understood?
Yes, sir.
So this
Yes,
will
sir.
be minus gm2 by g02, correct? So now can you understand? Now can you see what happened here because of the 0? Can you clearly see
Yes, yes, sir.
there was some delay?
Output is lagging the input.
Correct,
Yes.
correct. And what it is lacking because ideally, what did you want? Because of this unit step V in, you ideally wanted your system's response to be equal to what? GM2 by G02, right? Minus GM2 by G02 instantaneously. I mean, if the system would have jumped instantaneously to this value like this, then this was an ideal response. Okay, this would have been an ideal response without any delay. But this response took like a whole different approach because of the 0, right? Isn't it? And it went first in this direction. It first went in this negative opposite direction to where it should have settled, and then it started decreasing like this, isn't it?
Yes, sir.
So because of this right half plane 0, what happened? Instead of jumping in the basically instead of going in the correct direction, it took a wrong turn. Okay, it took a wrong turn in the wrong direction, and then when it realized, okay, I took a wrong turn, then it started coming back. So what does this 0 do? Right half plane 0 do here is that it gives an impetus to the system in a direction that is exactly opposite to where it should move toward. Do you understand?
Yes,
Can you
sir.
repeat that?
Yeah, so what this right half plane 0 is doing here is that, you see, if this 0 would not have been present, the ideal response of the system would be what? It would be like this, right? It will be simply when the input is applied here V in, it will simply jump to this minus gm2 by go2, right? Instantaneously. Is that clear? So Sibin, I guess Sibin was asking something.
Yeah, yeah,
Is this clear, Sibin?
yeah,
Yeah.
yeah.
So, but because of this 0, what happened? This 0 actually pushed the system in the opposite direction, isn't it? It pushed the system in the opposite direction, and then it realized that, okay, I have done a blunder. Then it started moving back to the to the right direction, right? Because of and this happened because of this 0. It pushed the system in the opposite direction to where it should have headed at the start. What was pole doing? You see this pole here? It is actually, the pole is not giving the system any opposite direction, right? When the input is moving here, the pole, because of the pole, the system is delayed, but it is actually moving in the same direction, right? As where it should go to, right, Sibin?
Okay, okay, okay.
Right.
Understand. Yes.
But what happened here? You see, because of the 0, what happened? This is a right half plane, by the way. Okay, right half plane 0 that I am talking about. Because of this right half plane 0, this system actually moved in the wrong direction. Okay, to where it should have gone, and then it realized that something is wrong, so then it started coming back in the correct direction. Okay, so that is
So,
why, you understood, Sibin?
so yeah. So it's because if it's taking that opposite direction, is that's the reason why the delay is coming,
Yeah,
right?
yeah, exactly. It's a very
Okay.
huge blunder that this 0 is introducing. Okay, the 0 is directly pushing the system in the opposite direction to where it should have headed. Okay, so that is why you can clearly, and you can clearly see the time domain response, right? Ideally, ideal response was like this, right? But it is taking like forever to settle down. So this is basically a delay, isn't it? And this delay is coming because of the 0. Correct?
Understood, sir.
Yeah.
Understood.
Now, what happens when we have a left half plane 0? Let's see. We know that left half plane 0 will add will basically aid system stability, right? This was a right half plane 0, right? If it would have been like this plus here, then it would have simply improved the phase margin, isn't it?
Yes, sir.
Yes,
So
sir.
let's see what happens when we have a left half plane 0. Okay, 0, yeah. So left half plane 0. So it will be something of this kind. LFS will be something like this. Or let's forget about LFS. Okay. Uh, let's again take the second path only. This example again. Oh shit.
Sir,
Yeah.
can I ask you a question about week 6 assignment?
1 second. Okay. First, let me finish this.
Okay, sir.
Okay. So now we saw that the system was simply being pushed in the wrong direction, right? So what can we do here to make sure that the system is pushed in the right direction? What change should we do?
We can add a register.
We can add a resistor. And how will that help?
I mean, in series of C.
Oh, you are adding. Yeah, correct. So that is true. Yes, that is true. That is the solution, right? But I am asking a more common. I mean, if you had not known about this zero cancelling register, what would have been the first? What would have been your first line of thought? So at least for me, my first line of thought was this: why don't we do this? This is plus, this is minus, instead of minus and plus. Okay. Is it
Yes, yes, yes,
right?
Yes, sir.
Correct. Now you see, now if you give an input here as a unit step here, the system will be pushed in this direction only, right? It will be C divided by
Yes.
C plus CL times V in, correct? And the final value that it has to settle to is actually equal to GM2 by G02 plus, right? So what happens here is that because of the because of this 0 here, there is again a 0 here, right? But because of that 0, what happens is that the system, let's say this is the input V in, okay, and what happens is that the system takes an initial jump here, okay, which is equal to C divided by C plus CL, okay, and then from here it slowly rises to this value, not to this value but to a different value, which is G divided by GM2 divided by G02, isn't it?
Yes, sir.
So this here, if you calculate also, you will see that this actually gives rise to uh, LHP 0. Okay, you can see this. But now you will ask me, so why do we do this? So why do we not simply change this signs here? You will ask me this question, right?
Yes, sir.
But because what happens is when you do that, you will mess up the poles, and the poles will become go in the will mess up the poles basically. Okay, you can check that. You can see that this will simply mess up the poles, and you will have an unstable system. Okay, but this was just to give you an insight on how the zeros change, how the zeros response looks like. Okay, because of any
Sir,
zero.
sir, also that second op amp is for current control, like second arrangement is for current control voltage source, no? So we actually cannot have
Yeah, yeah,
the
true.
feedback too.
No, 1 second. That is not actually true. Overall feedback should be negative feedback. Yes, you are right. Yeah, you are right. The second configuration is sorry. Yeah, the second configuration is actually for the current control. We are trying to implement a CCBS. Okay, so that is why. But yeah, I was just trying to give you a like feel of what happens. Yeah, you are right. I mean, you can definitely not change the signs here. Okay, that will cause a lot of problems. It will make the system unstable. But that this is what happens. You get a right half plane 0 in this way. So another way to see a left half plane 0 is this one. A very common exercise that you must have seen in your gate exams also. If you will give, you will also see in the gate exam interviews. This is a very common question. So this is an RC circuit, right?
Yes.
Correct? And you know that the system's response is like this. Okay? Now what happens when I do this? So let's yeah, so what happens when you do this? C2 and this is C1. I mean, what is the response? What is the transfer function between input and output? V out by V in. What is the transfer function?
Sir, in numerator there will be 1 plus s by like z on, where z on is the c2 1 by c2 in by r, 1 by c2 r actually.
Yeah,
That
correct,
is the 0, yes. And
correct,
there will be like one pole that is in denominator, like 1 plus parallel combination of c1 plus c2 into r.
correct.
Yes.
Definitely yes. So basically, you see that there is a zero here, right? And what is this zero's property? I mean, is this in the left half plane or right half plane?
Left up
Sir,
plane.
this is right, left up plane, like
Correct. So this
left.
zero is in LHP, right? This is a left half plane zero. Correct. So and
Yes, sir.
what is the response of the system to a unit step? Tell me.
So first of all, it will jump to C2 by C1 plus C2 and
Correct.
then settle to the value of V1.
Correct. So it will jump to the C2 by C1, C2 by C1 plus C2, and then it will slowly rise to the value. Which value? V in. Right.
On V.
V.
Correct. So basically, you see that because of the left LHP 0, the system is pushed in the right direction initially, right? You see, this system is pushed here in the right direction because of the LHP 0. But because of a right half plane 0, this system is simply pushed in the wrong direction, right? The system is pushed in the wrong direction here. Correct?
Yes.
So this is the intuition behind this poles and zeros, and how its response looks like in time domain. So this intuition comes in very handy. Okay. So that's it for today. And someone was trying to ask me something about assignment 6.
Yes, sir.
Yeah.
Sir, in the second problem, should we be doing the whole analysis with CC and without CC, two times with three poles and
What is this? Let's
everything?
see. So what is CC?
In the
With
fifth
CC?
question, they asked about a phase margin. So should be calculating we should be doing the analysis of the whole thing.
Yeah, yeah. I
Like
guess so. In the fifth question,
and
one, 2, 3, 4, 5.
from the sixth, we should attach CC and we should be doing the whole analysis again.
Oh, 1 second. Let me take that part. Okay. I'll share this. Let me take that.
So I have a doubt.
Yeah, yeah.
The when we try to find the answers for I bias, I1, IP, IN, and V offset, what's the last step that one needs to do to find those currents? We'll just get three equations and we need to
Yeah,
solve those three equations,
correct.
right?
Yes, yes.
But if we do it that way, won't the values just keep changing for different values of resistances that we use?
I don't think so. They will come out to be independent of that.
Okay.
Yeah. So, fifth question. What is the phase margin of the closed loop between the output node and the ground? Yeah, so what was your question?
Sir, should we be doing the whole analysis for the Miller capacitance circuit?
I don't think there's a Miller capacitance
The,
here.
no. Just like the same analysis, we should do it again. Should we do it again? like we need the pole frequencies. There are three poles, so
Right. I mean, whatever you are required to do,
like
you will have to do. I mean,
SQ,
I have not read this
etc.
question. Okay. But what is the DC frequency of DC loop gain? Yeah, so this is
That's
okay. What is the phase margin closed loop amplifier? When you put it in closed loop here, what is the phase margin? For that, you will have to find out the location of all the three poles. Okay,
yes, sir. Yes, sir.
right? And
Yes, sir.
that those three poles have to be found out again because you have added an extra capacitor here, right? See,
Okay, sir.
see a capacitor 1 picofarad. But I don't think this capacitor will change the location of the other two poles. It will only change the location of the first pole because this is not a Miller compensation. This is only a dominant pole compensation. Just simply
Oh,
put
sir.
between
From the sixth question, they added a CC. Sixth.
between the output node of I1 and ground. Yeah, so
That's
this
not a
is
Miller
still
capacitance,
this is
I
not a
guess.
Miller compensation, nah.
Yes,
This is
sir.
simply between output of I1 here and ground, right? This is simple capacitor here. So this will simply
Okay,
change the
okay.
pole of
Not the
this
ground
first.
of VS. Okay,
Yeah,
sir.
this will simply change
Okay.
the pole of this first I1 and not of this
Okay,
I2
okay.
and
Okay,
I3.
fine.
Okay.
And like, should we find out the whole with omega u loop or just omega u for the fourth question?
What is the fourth question? What is the low frequency gain of the op amp? Low frequency means DC gain, right?
Just omega u.
No, what do you understand by DC gain?
Like, I understood that it would be the whole a loop.
Yeah, so you have a loop right here also. You have to
Yes.
simply find out what is the loop gain in this case. What is the loop gain
But
of
the op amp is exactly combination of I1, I2, and I3.
yeah? So it looks like yeah, okay. So you are asking whether we have to take R2 and R1 into account or not for calculating loop
Yes.
gain. Is that what you are asking?
Yes, yes, sir.
Yeah, so I guess because in week 4 we had the same doubt, right? So maybe in this week you do not need to, I mean, maybe this is the same way, so you do not need to take this R2 and R1 into account. I mean, I cannot say, but I cannot guarantee it, okay? Again,
Okay, sir.
I cannot guarantee it. I mean, it may happen that because of this R2 and R1, I mean, it may happen that they want you to take this R2 and R1 into account. I mean, I cannot say.
Okay, sir.
These confusions you should raise these questions to, you can write to Professor Aniruddhan, okay?
Okay, sir. Okay, sir.
Fine.
Thank you, sir.
Yeah. So I guess that's it. Okay. So let's thank you all for coming today. So let's meet again
Thank you.
next Sunday. Okay.
Thank you. Thank you.
Thank you,
Yeah.
sir.
Sir, one
Yeah.
question, sir.
Yeah.
Sir, in week 7, sir, videos are from Krishnapur professor only, sir. Is it correct or not?
Yeah. It is. Yes.
Thank you.
Yeah. Fine. So let's meet again next Sunday. Thank you all for joining. Thank you. Let's see you again.
Thank you, sir.
Yeah.
Thank you,
Thank you,
sir.
sir.